Welcome to secondary steel making process. Today I am going to speak about thermodynamics which involves in secondary steel making processes. What is the importance of knowing thermodynamics in a secondary steel making process? In a ladle process, in a ladle the top portions, the top layer is slag. So in the bottom layer is below that, which the layer is molten metal. So what reactions are happening? So all about heat evolving, heat absorption and chemical reactions which gives out heat output is about thermodynamics. It means that there are dynamically the reactions are happening and heat. So the study about the heat and dynamics in the steel making is important to know at this stage. Molten slags. If you want to know about molten slags and its relation, its quantity, what is the activity of that particular slags element or compound, so the Raoults law is much useful to know all those things. In case of molten metal or hot metal such as steel made from the primary steel making, so how many impurities are dissolved, what is the content of impurity, it is calculated with respect to 100% standard state. With it 100%, 1 is nothing but one number indicates 100%. In that situation Henry's law is very much useful. So there are few things one need to know. If the bracket in the chemical reaction, if it is shown with this particular square bracket, it denotes that impurity dissolved in hot metal. If this is a bracket, simple bracket, impurity dissolved in slag. If this is a bracket, impurity dissolved gone into the gases. As you know that thermodynamic reaction or any chemical reactions, reactant gives rise products which gives rise some amount of free energy, the available energy which comes out, standard free energy plus RT, gas constant and temperature, and logarithmic of J is nothing but activity quotient, and standard free energy can be expressed in terms of minus RT ln J or K, which is equilibrium constant. For example, if the equation is this is a slag, this is a impurity dissolved in molten metal, impurity dissolved in molten metal, oxygen and iron. So you can calculate equilibrium constant, activity of FeO product by activities of reactants. Finally, it is assumed that activity of pure element in case of molten metal assumed as a unit T constant. Note this point. And this particular things gives you about how much oxides are removed, quantity, physical quantity you can know by these things. This is about Raoults law. The Raoults law says that if this is the reaction, the multiple of A, multiple of B, multiple of C, D, reactants and products, you can calculate similarly in this fashion. The Raoults law says that the activity dissolved in a slag is directly equal to mole fraction of that particular I element. If the solution is ideal, assume that there are no other impurities, then A of I equal to Xi. If it is non-ideal solution, if there are many impurities dissolved such as iron and manganese, iron and copper, so then gamma I, which is activity coefficient, is expressed. And finally, there are some statistically data and graph gives you that in case of copper activity in a slag gives positive deviation. If it is silicon, it gives negative deviation. Whereas this particular manganese gives straight line along this Raoults law. It gives like just like ideal solution. These things you need to note down. Physically, what this particular Raoults law gives, that the negative deviation, iron and silicon, the rest of the element is iron. So E is nothing but strong negative. It goes to the solution. And iron copper solution, strong tendency, the copper segregates along with the iron. And coming to the Henry's law, similarly Henry's law also suggests that Henryan activity, as AI is Raoults Law activity, HI is called as Henryan activity, is directly proportional to weight percentage. It's not mole fraction, weight percentage of ith element, or in another words ratio of Raoults Henryan activity and weight percentage is equal to 1. And there is a relation between the Raoults law and Henry's law. Henry's law gives maximum 1 weight percentage, whereas Raoults law there are many impurities dissolved in the slag, whereas in the case of molten metal very less. So that's why Henry's law is applied to that. This x-axis is weight percentage in case of Henry's law, and in case of Raoults law it is mole fraction. If it is the solution is ideal, it is equal to 1. If the solution is non-ideal solution, it is equal to Henryan coefficient. F of I is Henryan coefficient. So how do you calculate? In the case of molten metal also there will be many impurities which dissolves carbon, manganese, sulfur, phosphorus. How do you calculate with respect to the parent element? It is calculated with respect to the logarithmic of Henryan coefficient. E of I and E of j. I, j, k elements are solutes in the molten metal, and the top portion superscript is the parent element. So Henry's law for the ideal solution, non-ideal solution. And how do you calculate this Henryan coefficient? So similarly from the Raoults activity coefficient and Raoults activity coefficient. Let me take one example for calculation of Henry's law. So, for example, in the molten metal such as steel, the carbon is around 4%, silicon is around 1.5%. In that situation, so how do you calculate, how do you apply the Henry's law and Raoults law? So let us know with this particular example. So assume that the sulfur, Henryan activity of sulfur, Henryan coefficient of sulfur and weight percentage of sulfur can be written as, when you apply the Henryan law for the molten metal. And how do you calculate the Henryan coefficient? By logarithmic. This is the expression from the given data one can rewrite, and these particular values, exponent values, are interatomic coefficient or interaction parameters of sulfur with sulfur, and sulfur, how does sulfur react with the carbon, and sulfur with silicon. This is supposed to be subscript, please make a note. This is also supposed to be subscript, and sulfur reacts with the manganese. These are the thermodynamics data, and in a thermodynamics, metallurgical thermodynamics textbook, these values are available. So one can take out and one can solve. Mostly in any of the numerical problems, this will be as given data. And assume that these are the impurities dissolved in the molten metal. And how do you calculate for this particular sulfur? So as I said that for the Henry's law, this is for the solvent, the left side one, or LHS. RHS is related to the solutes dissolved in the molten metal. And this particular entire expression you can also calculate using a software called thermocalc software. Otherwise you need to apply the Taylor series and expand the equations. You need to apply the logarithmic and multiple logarithmic, and finally you will be getting the answer. This particular software gives you very easy way. So how do you calculate this particular things? This is one of the numerical problem. The answer for this particular Henryan coefficient is 10.75, and activity of sulfur, so as how much sulfur is dissolved or left with the diluted solution, is 0.43. It can be expanded. One of the numerical problem, so I will give you in the next series of the lecture. Thank you.